so you don't have to memorize what's on the screen right here. Okay, I'm going to start because this is a workshop where we do a deeper dive into the functions and how it all works. If you haven't seen the overview of IEEE 1815.2, I would advise you to go do that. This workshop will make more sense in those for that reason. I also will try to stop every now and again to get questions, particularly as we go through each of the items. So the contents are here. First, just a quick introduction to MESA Alliance and 1815.2. And then I'm going to focus on the spreadsheet, contents and layout, examples of the 1547 functions, not all of them, of course, but just examples to show how the spreadsheet and the document, the 1815.2 document, work together. And then I'm going to get into two tricky topics, which is the management of curves and the even trickier topic of management of scheduling. And then sort of membership information and any sort of general questions. So introduction, MESA is the Modular Energy System Architecture Standards Alliance. It's an industry association comprised of electric utilities and technology suppliers. And this is an image of the icons for all of the different members that we have so far. And as you can see, there's a very good mix of utilities as well as energy, as well as the manufacturers and vendors and integrators of these systems. So what exactly is 1815.2? It is a standard profile for communications with DERs using the 1815 standard, which is the DNP3 standard. So it's basically a profile for communications using DNP3. For those that don't know this, and I hope you do, DNP3 itself is very, very basic. It only includes analog values and binary values, inputs and outputs, and doesn't include any kind of names or semantics to go along with those points. And this is fine if you are a single utility and you are in charge of determining what the DNP3 points mean. But if you now have to integrate with many different DERs and the DER vendors have to integrate with many different utilities, it's really important to develop a profile, a standard profile, so that everybody will be using the same DNP3 points to mean the same things. So that's what 1815.2 is. So it establishes a standard profile for communications with DER or inverter-based resources, IBR. These are typically the larger systems using DNP3. So it is really critical to have such a standard, both for utilities as well as the manufacturers and integrators. The profile consists of high-level data model or DER communications based on selected data objects from IEC 61850-7-420, the 2021 data model. And the names from these 61850 data objects are mapped to fixed list of DNP3 data points for interoperability. It also has a number of other items, such as new functions going beyond the 1547 functions. It also meets the IEEE 2800, which are the larger inverter-based resource systems that may be transmission connected as well as distribution connected, because DER is typically distribution connected. And it also includes alarms, logs, historical records, and other types of data objects. So this is sort of a diagram that shows, I come in here with some circles around it. These are the areas where DNP3 and 1815.2 are important. I see I have, in a couple of instances, identified 2030.5, but it's really the 1815.2 that I wanted to reference. But you can see it, if you have a utility transmission system or distribution system that has a SCADA, that's going to directly interact with a DER, that's one area that is very conducive to using 1815.2. But it's also can be used for aggregators, interactions with aggregators, and interactions with the plants, the facility energy management systems themselves. It could also be used internally to DER systems, plants, and that's maybe valid for, say, microgrids, or if they're community virtual power plants, things like that, as opposed to a simple residential site, which was most likely going to use either Modbus or some proprietary protocol. So these are the different functions. I won't go through these other than to note that there are indeed many additional 1815.2 functions that go beyond the 1547, because in the 1815.2, we are indeed focused a lot on storage systems and management of systems, as well as just meeting the basic 1547 requirements. I won't go through this diagram in detail, but I want to point out here what 1815.2 really consists of. It consists essentially of two documents. One is a Word-based document, obviously PDF, but the other, and that has, you know, all of the typical descriptions and so forth, but it also consists of a spreadsheet, so that it becomes, the spreadsheet, it becomes an electronic source for the normative standard. We'll see exactly what the IEEE allows to have for this, but the reality is that it's going to be the spreadsheet that provides most of the normative information that's electronically available. So you don't have to copy and paste. You can actually download from the spreadsheet. It's not as good as maybe some other types of sources, but it at least is there from the perspective of being electronic source. This is a table of contents. I will not go through this, but as you can see, just in general, there's sort of some introductory material, and then there's the list of the DER functions, so that it's each one of these functions is described in detail, including what data points, DNP3 data points, are involved in it. Okay, so just going back a moment here, are there any questions so far? Okay. Going forward, I'm now going to get more into the spreadsheet itself because that's what's, in a sense, novel about this standard. The spreadsheet consists of a number of tabs, as typical for a spreadsheet. And it defines very, very clearly each of the points that are required for this, meeting all of the functions that I showed previously. It has, in essence, four, we can say five, but most four tabs that are really of interest to this group. There's the binary output tab, the binary input tab, the analog output tab, and the analog input tab. And the starting index shows where the DNP3 points start. So it starts at point 0 and it goes on directly from there. So each one of these is where the range of points are located. And then schedules jumps to a new index because we wanted to leave room for future extensions. So we just sort of have left a blank between that, and now we're jumping to 2000. And for some new schedules, I'll get into all of this, at 3000. Then we have, again, a gap and historical points, all with these types of indexes, because we don't know at the start how many data points, historical data points, are needed. You know, do you have one battery or do you have 10 batteries? You know, whatever. Okay, any questions about this? I will get into more detail, but any questions about this tab here? Okay, so this is an example of what the spreadsheet looks like. This is the binary output, or part of the binary output spreadsheet. It consists of a DNP3 point index over here on the left. And as you can see, it starts at binary output 0, binary output 1, binary output 2, etc. It just goes right down the list of binary output points. And then we have the name and the description, a little more information, and then a unique string that comes from 61850 that defines the meaning of the point. Here we just have a description, but here we have a unique string. So the important aspects of this spreadsheet are the DNP3 point index and the corresponding unique string from 61850. So of course we have additional information, useful information, and some additional definitions. What does it mean when it's 0? What does it mean when it's a 1? But the key point are these two. There's this correlation between the unique string and the DNP3 point. The same here is true for analog inputs. I'm just using these as examples. Again, starting the DNP3 points from AI, analog input 0, and it continues on up. And here is the unique 61850 string that correlates with it. Again, there's additional information about maximum and minimum, whether there's a scaling multiplier or an offset. And again, some additional information about what its purpose is, whether it's included in 1547. So there's a lot of additional information, but the key profile are these two columns here. Let me just go back and ask, are there any questions so far? Okay. we'll keep going. So in the document itself, there is a table, table 1, that overviews all of the functions in 1815.2. And so you see here the list of the functions, some of the configuration stuff, and then we get into some of the functions themselves. And then a brief description, and then where it's covered in the document itself, down here, and what the DNP3 points are associated with that function or that set of items. So this provides a very useful way of saying, okay, well, if I want to do, let's say, active power limiting, that's down here, you see exactly what clause to go to, and you see what points there are that you need to cover, and that these would be in the spreadsheet. So these are essentially the spreadsheet numbers. Okay, any final or any comments again on this just overview of what the spreadsheet looks like in itself, and how it's correlated with the document, the sort of Word document? Okay, moving right along. Okay, so I'm going to cover as examples some of the functions that are used for 1547, so that you can see how this is used. So starting with the active power limit function, we see that the spreadsheet, and again, you can see here the data points and the 61850 names, unique names, that are associated with the active power function itself. And there are a number of points here. I don't expect everybody to be able to read everything that's in here. You need to look at it yourself, but I'll just say that there's a priority for the function. There's a time window, a ramp rate, a reversion timeout period. If nothing more, it's going to go on forever, or should it revert back to normal after a particular time? And then where is the signal meter that you're going to pick up the information? Is it going to be the PCC, point of common coupling to the grid, or is it going to be some other point, reference point of applicability that you want to have the limit function apply to? And then there's a point where the input to the active power function, where does that come from? Is it going to be the same location as the meter that is where you want to limit it to, or where is the information coming from? It may come from the same meter, or it may come from a different meter. And then the most obvious things, the limit itself, the charge limit, and the generation set point that you want to have for discharging. So these are the spreadsheet points. In the document itself, it helps as part of the description exactly what to do. You should set the priority if you haven't already. You set enabling time window, ramp time, and timeout. You set the meter. You reference the maximum actual active power capacity and the maximum output in watts, and then you enable the function. So these are the steps that you need to do to actually use this function. And then here are just some illustrations of what you're doing. You set a high limit and a low limit, and it could be up in the generation area, because this is the generation area, or it could be in the charging or load area. Okay, so it's a high limit and a low limit. And or it could be a limit for generation and a lower limit for charging. So you could go anywhere within this, just so long as you meet the charging upper limit, or sorry, the discharging upper limit and the charging lower limit. This is, I won't go through this one in gory detail because there's a lot of points, but this is essentially the frequency water droop function. Again, another 1547 type function, which you can see from this diagram here. So again, it's a matter of setting the priority, a bunch of other stuff, the high starting frequency, the high stopping frequency, where should you just stop increasing or decreasing, the discharging gradient and the charging, so the discharging gradient and the charging gradient, and the equivalent for the low point. So the low, oops, this is frequency, the low frequency versus the high frequency. So as you can see, we have all the points in the spreadsheet so that you can see what they are and their maximum and minimums, the units, the multipliers, and all of the other information that you need. A function that's not in 1547, but I think could become increasingly important, is the peak power limiting. That's fairly commonly understood, but also load following and generation following functions. They're similar in a lot of ways, so we've included them as having the same items, but just different point numbers. So again, the DNP3 points here. But the idea here with the peak power limiting is pretty straightforward. If you want to limit, let's say, the load, you want to turn the battery on or increase the power of the battery to follow what the load would have been doing, but end up having then just this limit and then going down below. So this is a fairly common item that's not directly in 1547 because it doesn't look at loads, but it's really important, I think, in the future when we're going to be doing power limiting of loads. I'll get into that one a little bit later. Generation following is pretty similar in that what we're doing is saying, okay, we've got some kind of generation that's following the load so that the actual output is flattened. There's a way of doing it on a percentage basis or something, but it's basically saying I am going to follow the load by generation so that I can compensate for the load and fluctuations in the load to make it just meet a certain level or area, because it's not necessarily a limit, it's just an area. The same is true for following by generation following by, let's say, storage generation. So here you have the storage, and here you have PV generation. But as you can see, there are variations, fluctuations in the PV, and you may have a limit that you need to meet. And so you're going to charge your storage where it needs to compensate for the PV, or it could be discharge if you're trying to do something else. But it's basically saying, okay, I've got a generation system and a storage system, and I'm going to make them work together to do what I would really like the whole system to be able to do. So we do have these two functions as well as the peak power limiting function. Another one which is new is synthetic inertia. And it uses, in this case, sort of a simplified delta frequency, delta time approach, kind of Rokoff, but to defining a synthetic inertia derivative factor. I won't go into the, the power engineering of this. And I know there are going to be other synthetic inertia type functions. So this was just a first pass at doing a sort of a basic one that can meet many of the requirements for synthetic inertia. So this goes beyond droop, which is droop does a sort of a direct response. This is more the response to the rate of change of frequency, so Rokoff. But again, you can see that we have the points in the spreadsheet and then the steps here in the document itself that says exactly what you're going to do and how you're going and what points you need to put in, and maybe in this case some specific values. This is these diagrams, tables are for those people that know DNP3 extremely well. I am not going to go through them, but the point that I'm making here is that these are included in the 1815.2 document to define very, very clearly what DNP3 characteristics there are for different points. So this is important for the DNP3 experts. Okay, I'll stop here again and see if there are any questions. Okay, moving right along. I'm going to get into the management of curves. If you remember, DNP3 is just a set of points, 1, 2, 3, 4, 5, 6, 7, etc. So one of the issues that has come up is if you have a set of points that you don't know how many there would be or could be in any particular situation, you have to do something a little bit different. So in a particular function, you could have a set point, and so that would be one DNP3 point. But if you have a curve, and let me just go to the this diagram here, you can see a basic volt-var curve, and it consists of multiple points, or if it's even more complex, it can consist of quite a few points. So how do you handle the fact that you could have, 4 or 5 points, or maybe 6 or 7 or 8 points, and then maybe some other values or functions? There could be 10 or 20 different points to define the particular curve that you want. So going back here, what we've done is said, okay, we'll have a special section of DNP3 points that reflect a curve, but it could be for any curve. So we say, okay, the curve contains, what is the curve for? Is it for the volt-var function? Is it for the frequency watt function? So you set the type of curve. I'll get into what the selector means in a moment. And you say, okay, is it temperature? Is it pricing signal? What are the different types of curves that you're talking about, because that may affect what it looks like. And then you have the two values that are in a curve, the x value and the y value. So here, the x value may be time, It may be voltage, it may be frequency or watts. And the Y value may be VARs as a percentage of max, VARs as a percentage of max watts, power factor, frequency as a percent of nominal frequency. So there are many types of Y values, but you can establish those. And then you put them into the different curve points that, again, we have here is the DNP 3 point, A0249 is the first one. And you have two values. You have the X value and the Y value. And then you have the second X value and Y value. And the third point, X value and Y value, and so forth. We've allowed 100 points just because that was a way of doing it. But down here, and you can just see it at the bottom of the screen on the left here, is the number of points that you're actually going to do. So you may just stop it at 6 points or 4 points or whatever it is, the number of points that you need. Okay, but this is one set of DNP 3 points. Okay. How do you say, well, I want to do a volt-var curve, but I also want to do a voltage-watt curve? How do I use the same set of points to do two different things? And that's where we come into the selector mechanism for setting and updating curves. So we have the selector item. I mentioned it a moment ago. But that selector point determines which curve is visible, in a sense, to the controlling station at any time. So just going back for a moment here, we have the curve selector. And if the curve selector is number 1, let's just say that's the for a volt-var function curve. And selector number 29 is for temperature mode, etc. So this is entirely up to implementations as to which selector number is associated with which curve, because some people may have 2 or 3 volt-var curves, and you assign different selector numbers to each one of those curves. So we didn't assign anything to a particular type of curve. We just said, okay, there's a selector for it. So coming down here, how does this work? So you select the which curve you want to make, quote, visible, and then you establish whether it's being referenced by a DER function like the volt-var curve, or is it reserved, but you haven't set the points yet. You just sort of reserved it. You want to, establish this for future use, or the curve is not in use. It's empty, and that's just a 0. Okay, but what you do to create a new curve, the controlling station performs the following steps. It selects the index number that is not in use, so it's blank or can be one that's already in use, but you know what it is that you want. It modifies the points. So this is the curve functions, the X values, and the Y values for each curve. And then it so these then become a block of curves, and then it selects the curve in the analog output settings for the appropriate function. So again, we set it to being the volt-var curve. That says, okay, we want to use curve index number 23 for the volt-var curve. And then it enables the function. So looking at this diagram, there's sort of this selector. You select it, and then you say, okay, I have selected, in this case, we're looking at curve number 3. So you then put in all of this information into here, and then the outstation essentially stores it away somewhere. We don't say where or how. That's beyond DNP3. But that curve is then established somewhere by the outstation. And then you can do a curve selector for, let's say, curve number 2, and do the same thing and put in new values. So we're basically using the same set of DNP3 points to input or update the curve values for each of the functions by having this selector number that then references them. Any questions here? This can be a little complicated if it's the first time you've seen it. Okay, we'll go on from here. Again, an example of this where the volt-var steps, I just picked up the ones that are related to the curves. I showed you these diagrams before where you have a curve associated with the function, and it could be simple or more complex. And so you select which curve to edit. You specify the curve mode, in this case, volt-var. You set the X values, you set the Y values. You can set percentages for those as well. And then you set the number of points used for the curve, and then some other items associated with curves. And then you enable the volt-var function. So this is how you use curves where you have an undefined number of points associated with a particular function. You just use them again and again and again by selecting different blocks of them. Okay, any questions again on curves? Okay, so let's get into scheduling a little bit. In the past, there quite frankly wasn't terribly much use for scheduling between, say, a utility and a DER, or even between, an aggregator, say, and a DER. But what's been happening, at least in California and certainly in Hawaii and other states or territories that have islands, including ones that are almost islands, like long peninsulas or tricky areas where you have limited ability to increase the capacity, let's say, of a transmission line or a distribution line. It's becoming critical to be able to limit the export of power. So this is now power. So we're talking about export power limiting, as well as now with data centers and AI and EV charging stations and other big hungry loads, there will also be a need to limit imports. But it's not, today's a utility may say, well, I need to import limit or have an export limit of a certain amount or an import limit of a certain amount, and you can sign a contract for that limit. But tomorrow, there may be the ability to export more than that limit or to import more than that limit. Nobody knows, because it's a very dynamically changing set of requirements. So one of the things we're proposing, it's still just a proposition, we're proposing in California is to include non-firm export capacity and non-firm import capacity that says, okay, you can give me a firm export limit. Let's just talk about export at the moment. You can give me a firm export limit, but I have more ability, more capacity to export it. And if authorized by the distribution utility, they can export more. So the DSO, the distribution system operator, can look at current or forecast grid conditions or weather forecasts and power flows and all of that kind of information that they will be able to do in the future with their DERMS. Most utilities cannot, distribution utilities can't do that now. But that's certainly true that in the future, the distribution utilities will also be able to do that. Then they can authorize the generation power plants to export more. And this may be based on a schedule, and I will show you here some examples of that. But first, just ignore the minimum export requirement at the moment. But UL 3141 is developing testing requirements for scheduling of import and export limits. So this is something that is going on and is becoming well accepted. Okay, so here's an example of firm and non-firm limits. So you have the red here is what the utility has determined based on some of its own power flow information from historical records. And history at this point is changing rapidly, but so they have historical records. And so they've come up with this red set of requirements, different in December and January than it is in June and July, for whatever reasons. And that's their firm export limit for a particular customer, for a particular DER facility, okay? But the facility itself may be able to export more. And when the utility looks at, let's say day ahead or month ahead or week ahead, day ahead, or even hour ahead, it might be able to determine that indeed there is more room, more capacity on the grid to allow additional export. And that's what these purple lines are, to say, okay, we actually could export more given the current forecasts, weather forecasts, grid conditions, and all of that. And so what you're seeing here in this diagram, it's just sort of on a monthly basis because that's where we're starting. But in reality, it could be, as I said, on a weekly basis or week ahead basis, day ahead basis, or even an hour ahead basis, where these limits could change. So we need the ability to establish schedules of these. You don't want to just have the utility say, okay, at this moment you can have this amount, and the next moment you might have a different amount. You want to be able to schedule it so that the DER sites have some knowledge of what's going to be available so that they can plan ahead. So it's important not to just say all of this happens in real time. We're really talking about, as I said, week ahead, day ahead, or even hour ahead type information based on schedules. So given that, 1815.2 has improved its older scheduling capability, because when it was first developed as DNP3 app note, scheduling was not particularly important, and so did not have all the capabilities that we now know need to be done. But so we have vastly improved this 1815.2 scheduling capabilities, and now we have a full set of capabilities. First, I will point out, and as you can see from this drawing, the selector method is also used for scheduling. So you can select which schedule you want to edit. So you can see that it's the same process of using a fixed set of DNP3 points, and you sort of select which particular schedule you're working on. So first of all, there is an unlimited number of schedules. There's nothing that limits them. We do say that the first 100 have directly accessible status records so that they're easier to see, but you can always get the information from just going to the schedule itself. So this schedule, each schedule has a start date and time. And the time is delta seconds from midnight of the start date. There's a stop date and time. And then there are up to 100 steps per schedule, consisting of the delta time from the start time. So you might start at midnight, but your first scheduled event or function might be at 6 a.m. or at 2 p.m. or something like that. So you have the delta time from the start time, and then you would have, for different points in the schedule, you would have something that starts at 6 a.m., another event starts at 9 a.m., another event starts at 9:30, another event starts at 4 p.m. So that there are 100 steps, so you can have 100 up to 100 per schedule of items that might take place during the day or whenever. So you have the delta time. When is it going to take place? Then the action type, is it a binary or analog value? This is because DNP3 works as having either binary or analog. And so you always have to be able to tell the system which it is. And then you have the data objects DNP3 index. So are we going to do the volt-var function? Are we scheduling the volt-var function? Are we scheduling, frequency watt, droop? Are we, so these are, you have to have, what function it is that you are scheduling. And then you have the value of the data point that goes into the data objects index. So we also say that schedules may include actions that occur at the same time and include actions from one or more functions. We don't say it's just, here's a schedule for volt-var and there's a separate schedule for frequency watt. You can mix them if you want to. It may or may not be a good idea, but that's up to the designer. Schedules may be set to repeat by the number of minutes, by the number of hours, by days, by day of the week, by month, by year. Multiple schedules may be active at the same time. Priority of schedules, this is an important one. Priorities of schedules determine which actions will be executed if the values in the schedules are mutually exclusive. So that's an important factor, because we've got to make sure that the system knows which one to do. If they're both saying change the output of watts, you have to know which function to listen to, so therefore which schedule to listen to. So again, the types of values can be analog settings, can be active, can be ramp rates, you can change the priority of a function. There's a lot of things that you can change. Binary functions include the enabling, disabling, and a few binary commands. And all of these would be time-stamped events that are captured in logs. Okay, we also have a state machine of scheduling. I will not go through this particularly, but I think it's important to show that indeed the controlling station will start a new schedule and put it in. The outstation will determine whether there's a problem with it and send it back if there's a problem. If there's no problem with the schedule, it'll go on and say, hey, it's been validated. Okay, but it may not be running yet because remember, you have a start time, a start date and a start time. You'll go down to the enabled state. If the controlling station enables the schedule, that's a separate thing. And then it will go to the running state if the date and time is set to run. And then if its cycle is completed, it's a single one. Then if it's just a single one, it goes up to the disable state. If it's a cycle and there's going to be more, it's going to run every Tuesday. It will go back to the enabled state and wait for the next Tuesday to start running again. And then there's error conditions and expired and so forth. I won't go into those. But the point is that there is a very clear set of states that the schedule can be in so that at all times, both the outstation and the controlling station know what's going on and who's doing what. Again, just looking now at what's in the spreadsheet, as you can see, these are the scheduled data points starting at AO 3000. It has a set of items such as the priority. Again, the edit selector, important, so you know which one you're working with. Start date, start time, stop date, stop time, repeat interval. What kind of repeat you're going to do? Is it going to be on a minutes basis, second? Well, I don't know how many will do seconds, but anyway, minutes basis, days basis, weeks basis, and so forth. And you can cause it to repeat on the day of the week. So you can have it repeating on Sundays or Sundays and Saturdays, or you can have it repeating Mondays, Wednesdays, and Fridays, whatever, you know, the settings are here. And again, I mentioned that there are these 4 points that in each item, each schedule item, which is the offset, the action type, the index type, AO or BO, and the value. And here you see that. So the point number 1 consists of these 4 items. Point number 2 consists of these, etc. And then there's a way of seeing the status of what's happening. These are AI values, analog input values, where you see the status based on that state machine that I just showed you. And it will show you the priority, what the active step number is, and the actual status of the point. So, and here is just then a quick overview of an example. Getting pretty close to the end of time. So we have the priority. These are the dynamic volt-watt parameters. So there's a whole bunch of parameters. You set them in. You can say, okay, I'm going to start at 6 a.m. in the morning. And so you set all of these parameters in to be effective at 6 a.m. And then you say, okay, at 6 a.m., I'm going to enable it. You could have enabled it at a different time, but let's just say you put them all in at 6 a.m. and you enable it at 6 a.m. But then at noon, you change something, or you put it in so that at noon it will take a different value. And then at 9 p.m., it'll disable the function. And at 11 p.m., it'll stop the schedule. I haven't shown in here anything to do with repeats because I just kept it at a simple level. A quick example of combining schedules where you can see, I won't go through the details, but what you can see is that you can combine different functions so that they sort of work together to come up with a result that you want. You can set some upper limits that says you can't go beyond this because my equipment won't go beyond it. But then you use peak power limiting or generation following or active power smoothing to just sort of set, okay, what it is that you're actually going to do and come up with some kind of result. So membership with MESA, these are the important numbers, and I will go on directly to questions. So any final questions in the last minute that we have? Okay, I don't hear any questions. Again, I'm reiterating that the ballot pool is open, and this is the methodology for, first of all, becoming a member of the IEEE Standards Association, and then joining the ballot pool. Okay, if there are no questions, thank you very much for listening to this. And I hope that you've learned something from it. It can be confusing if this is the first time you've looked at the spreadsheet and the scheduling and curves and all of that. But I think it's important to get a sense of how 1815.2 works, because that's quite important. So thank you all for joining in. And if you have additional questions, please feel free to contact me or to contact MESA. And I appreciate you all for listening.